Hey, happy Friday, everyone. Welcome to Howlin at the Moon Science Friday number 2. This week we're going to talk about rainbows. And in about 10 minutes, you're going to know everything that there is to know functionally about how rainbows form. Now, this is another one of those kind of things that I had the opportunity to teach in 3 classes that I taught in my 25 years in higher education. I used to teach about rainbows in astronomy, I used to teach about them in meteorology, and I used to teach about them in engineering physics. And I approached them in slightly different ways in all 3 of those courses, but I'm going to weave together some common themes in a way that I think will be comprehensible to all of you without any mathematics. Now, rainbows are a common phenomenon. Everybody knows what a rainbow is, but hardly anybody knows how they form. And that's what I want to try to do today. Again, 10 minutes or less, I want you to understand almost everything that you need to know about how rainbows form and why they form. Now, there's 3 or 4 things that we need to talk about before we can actually start talking about rainbows. And we need to define some terms. Now, we talked about last week refraction and scattering, and we're not going to talk about scattering this week because it's insignificant in terms of rainbow formation or observation, but we are going to talk about refraction once again. And refraction, as you recall, is the bending of light when it goes from a less dense medium to a more dense medium. So when light comes from the vacuum of space into our atmosphere, air is denser than the vacuum of space, so the light bends a little bit. And not all of the wavelengths bend the same way. That's why when you pass light through a prism, it splits out into a rainbow. It does the same thing when you send it through raindrops. It splits out into a rainbow. And it turns out that the red slows down at a different rate than the blue slows down, and that's what causes that separation. So you get white light going into one side of a prism or a raindrop or anything else that can quote-unquote refract light. And the different wavelengths that compose white light. Remember, white light is a roughly equal blending of all of the colors of the spectrum, from violet all the way up to a deep dark red. You combine all those colors together with roughly equal intensity, you get white light. You pass them through a prism or any other refractory medium, and it separates those components out into a rainbow of colors, a continuous spectrum of colors. So, the second thing we got to talk about is something we didn't really talk about last week, which is reflection. And we talked about it a little bit last week, but not the way we're going to talk about it this week. Reflection is when something causes light to change its direction in a geometric manner, sort of like a basketball bounce pass. So if a beam of light hits, for instance, a mirror or the water or anything else at one angle, it bounces off at exactly the same angle, just like a basketball bounce pass when you throw it down the basketball court. That obeys something called the geometric law of reflection. Well, we discussed that last week. We talked about the 2 types of reflection, diffuse and specular. This week, what I want to talk about is something called total internal reflection, which is when light is in a dense medium, like water, and it's trying to go to a less dense medium, like air. At certain angles, it doesn't actually cross the boundary. It gets reflected entirely off the boundary and stays in the same medium. That's something called total internal reflection. It happens in prisms, and it happens in raindrops at certain angles of incidence. So, as you can see from the diagram up here, there are 4 things that have to occur during the formation of during the formation of a rainbow and your ability to view the rainbow. The first is a refraction that occurs as the light which comes in from over your shoulder. The geometry of a rainbow is that the sun has to be behind you and the rain has to be in front of you. So the light from the sun comes over your shoulder. It enters the raindrops. As it enters those raindrops, it undergoes first a refraction at the leading edge of the raindrop, and you can see that in the diagram above. As it undergoes that refraction, the red and blues bend at different angles because they slow down at different rates. They travel through the raindrops, now separated, but they're reflected off the back of the raindrop. And since they're trying to go from a more dense to a less dense medium, at the angle of refraction at which they hit, they don't ever cross the boundary. They're reflected. It's total internal reflection. So the beams of light stay entirely within the raindrop. There's no transmission across that back boundary. They're reflected back to the leading edge of the raindrop once again from where they came from, except lower. And they're refracted once again as they pass that raindrop back out into the air, pass that surface of the raindrop back out into the air. Now, as you can see in the diagram, the way all that works is that the blues come out on top and the reds come out underneath by the time they undergo this journey from the first refraction to the reflection off the back of the raindrop to the second refraction at the leading edge of the raindrop. So that's how a rainbow is formed, but it leaves a big mystery. If you're looking at the diagrams here, you would conclude that when you look at a rainbow, the blue and violet colors should be on the top and the red and orange colors should be at the bottom, but that's not the way a rainbow looks, is it? If you look at nature, it's exactly the opposite of what you see. You see the reds on the top, the long wavelengths on the top, and the shorter wavelengths on the bottom. Now, this is the thing everybody leaves out of their explanation of a rainbow. And to prepare for this, I actually did an internet search and looked around. And same as it was when I was teaching this, a half dozen years or so ago. Last time I ever taught a class. You could never find this last part, which explains why the order is reversed. There's a reversal of order in the rainbow that you observe over which you would expect to observe. Well, here's the reason for that. And again, there's the last diagram up here explains that. When those rays of light diverge from that raindrop, when they come out of the leading edge of the raindrop after the second refraction, they're spreading out again. Your eyeball is not big enough to see light as it spreads out, all coming from the same raindrop. It spreads out at too great of an angle, and I show that down there in the stick figure at the bottom. So if you look at that stick figure at the bottom, up here, I'm looking over here because I've got it down here as I'm talking to you. The red light that comes in, the red light and the blue light out of a single raindrop, they spread at such a great angle they can't both enter your eye at the same time. Your eye is very small compared to the spread of that light. So the red light that comes into your eye is coming from raindrops that are above the raindrops that are producing the blue light that comes into your eye. And a more general thing is that the longer wavelengths are coming from higher raindrops than the shorter wavelengths, which are coming from lower raindrops. So you experience reversal in the order. And that's why the rainbow has the reversal of the order that you would expect. So again, I want to keep this short because we said we were going to try to keep these things really quick so you can get through them fast, but still make you smarter than you were before you started watching this. So the light comes over your shoulder. It enters those raindrops. As the light enters the raindrops, it's refracted. So the white light gets separated, and the reds and the blues get separated at different angles. They pass through the raindrop, now separated. They hit the back of the raindrop, the side opposite that they came into the raindrop, and they undergo something called total internal reflection. So they don't go through the raindrop. They get reflected off the back side of the raindrop, back out the front side where they came from, but lower down in the raindrop. And you can see that in the diagrams. Now, they continue to spread out as they head towards the ground where the observer is. And because they continue to spread out, and your eye is actually very small compared to the spread that these rays of light are undergoing because the raindrops are typically pretty far away, you don't see all of the light being emitted by a single raindrop. You see light being emitted by multiple raindrops. And it turns out that the longer wavelengths are coming from higher raindrops than the shorter wavelengths, which are coming from lower raindrops. Hence the reversal of colors in the rainbow over what you would expect. If you look at a prism, it looks differently. The order of colors is different than it is in a rainbow. So there you go. 10 minutes or less, how a rainbow forms. Science Friday, Howlin at the Moon, number 2. I'll be back next week with another one. This is the last freebie, though. Next week, this is going to be a service for premium subscribers only. Be seeing you. Cheers.